I'm going to do just kind of a quick little run through of what we mean by this derivative and all this notation. So I would suggest just watch this video and you don't have to take any notes on it. Hopefully it'll help kind of clarify some of the muddiness of all the notation and stuff. So suppose we have this function y equals x squared, and we would like to find the slope of the tangent line to that function at the point 2, 4. So we're going to think of 2, 4 as kind of being our anchor point. And we're going to approximate that by finding the slopes of different secant lines at various points. So I've listed some of these in green. 636 is a different point on the curve, so we're talking about way up here, and we're going to be looking at the slope of the secant line, the line that connects those 2 points. So to do that, we're going to go, y2, 36 minus y1, 4 over 6 minus 2. And so that slope of the secant line, that's going to be 32 divided by 4 is going to be 8. And then we'll do that for 5, 25. So we'll go 25, the y-coordinate, minus 4, the y-coordinate of our anchor point, over 5, the x-coordinate, minus 2. So that's going to be 21 over 3, which is going to be 7. Then we'll choose the next one. So we'll go 9, and then minus the 4, and 3 minus the 2, and that's going to be 5 over 1, or 5. We'll go in the other direction, so we'll look at the slope of that secant line that's going to go between 0, 0 and our point 2, 4. So if we go 0 minus the 4 and 0 minus the 2, we'll get negative 4 over negative 2, which is positive 2. And if we use the point, I skipped one over there. So 1 minus the 4 and negative 1 minus the 2 is going to be negative 3 over negative 3 is going to be positive 1. And I'm going to try to fit this one in there. So if we go 1 minus 4 over 1 minus 2, that's going to be negative 3 over 1 is negative 3. So we see all these secant lines. So then we can say, well, in general, if we look at a formula, we would say, well, let's look at the slope of the secant line between 2, 4, and any other point on that line is going to be 2 plus h, where we're going to move some distance away from 2. And then what we would get is, for the y-coordinate, is going to be then just f of 2 plus h. And so then our slope of our secant line would be, well, let's see, if we plug in the 2 plus h, that's going to be 2 plus h squared, minus our y-coordinate is going to be 4, and then we'll have the 2 plus h minus our x-coordinate, 2. And so if we multiply that out, we'll get the first one squared, twice the product, plus the second one squared. Hopefully this looks a little familiar. And we'll see the 4's will cancel. We'll factor out that h, which will then cancel. And so the slope of our secant line is 4 plus h. This is like a formula. So you could pick h to be whatever you want. So for example, if we picked h to be equal to 1, that would be 1 away. Well, let's see, that would be right here. And so if we plugged in 1, we would get 4 plus 1 is 5. And that's exactly what we got by using that h to be 1. If we chose h to be, say, negative 2, then our point 2 plus negative 2 would be 0. So our formula would say it would be 4 plus our h would be negative 2. So our slope would be 4 plus the negative 2 would be 2. And 0, 0 is that point that's 2 to the left, and that's exactly what we got for that slope. So that would be a formula for the slope of our secant line to that point. So if we wanted to make it the tangent, if we wanted to make that the tangent line, then of course what we would do is take the limit as h goes to 0 of our formula, the 4 plus h, and that would be 4. And so that would be the actual slope of the tangent line to this one function, f of x equals x squared, at this one point, 2, 4. Well, what if we wanted it at a different point? So if we chose the point 3, 9 to be our anchor point, well, I think you can see that our formula for the secant line would then be that the slope would be, we would be taking that our point would be, our anchor point is 3, 9, and the other point would be 3 plus h and f of 3 plus h. And so that would be 3 plus h and 3 plus h squared, since our, that's not equals right here, that's our function is the x squared function, and so then the slope of our secant line would be that 3, can't write my 3's, the 3 plus h squared, that's the y coordinate of our generic point, minus the 9, that was our y value at our anchor point, and then the 3 plus h minus the 3. And so again, we would get 9 plus twice the product is 6h, plus the h squared minus 9 all over h. And our secant line then, after we cancel those 9's, and then also factor out that h, so that would leave us with 6, I believe, plus h, and cancel those. So our formula for the secant line to from any point on the y equals x squared curve to 3, 9 would be given by that formula 6 plus h. And then of course if we wanted to move to the slope of the tangent line, then what we would do is take that limit as h goes to 0 of our formula from the secant line, and that would give us 6. So then we might say, well, what if we don't want to just do it with the function f of x equals x squared? What if we would like to choose a different function, maybe 1 over x? And maybe for that, what we want to do is choose that, or let me back up a little bit. So let me do this. Suppose we don't want to be just using any particular point, but we want to take a point in general. So a point in general, still on the f of x equals x squared curve, would be our anchor point is going to be x squared. So that's any point we want that's on that parabola y equals x squared. And then our other point, some point a distance away, is going to be x plus h if we move h away from x, and its y coordinate will be x plus h squared. And so the slope of the secant line joining these 2 points, one that's at x squared and one that's h away from x, is going to be that x plus h squared minus x squared all over x plus h minus x. And so again, multiplying that out, we're going to get to the x squareds will cancel, and we'll factor that h out, and then that's going to be our slope of the secant line. So that's a formula. So you could pick whatever you wanted for x. So for example, if we chose x to be equal to 2, like we did in that first example, then our point would be 2, 4. And if we chose the h to be, say, if we want to move over to 6, we could say h was 4. That's going to be 4 away from 2. That would give us that second point of 636. And our formula would say we're going to get that the slope of that secant line would be 2x plus h, and we would have chosen 2 for the value of x and 4 for the value of h, which would make that slope of the secant line be 8. And if you see, that's exactly what we did over there. And then, of course, if we take the limit as h goes to 0, then our formula for the slope of the secant line becomes the slope of the tangent line, and that's where we get the 2x, which is our derivative of x squared. So then, if we want to say, well, I don't want limited to just f of x equals x squared and any point on there, I want to pick any function at all. And so then, of course, if we want to also choose, so this now is any function, and if we want to take any point as our anchor point, that is the point where we want to find the slope of the tangent line, then of course its coordinate will be x for the x-coordinate, and because it's on that any function we like curve f of x, that will make it be f of x for the y-coordinate. And if we take another point a little ways away, that will be h away from x, and again, h could be positive or negative, and that will make its y-coordinate be f of x plus h. And so our slope of the secant line is going to be that f of x plus h minus f of x all over the x plus h minus x, which is, of course, our difference quotient. And again, that is a formula for the slope of the secant line of between any point, so any point on any function. And to move from secant line to the tangent line, then what we do is take that limit as h goes to 0 of f of x plus h minus f of x all over h, and that's what we've been calling f prime of x, the derivative. I don't know. I hope that helps a little bit.